Voyager crossed what headlines call a 50,000-degree reader plasma barrier at the edge of the solar system, and it didn't melt. Even more mind-bending, the moment it touched that boundary, Earth only learned about it roughly 17 hours later, because Voyager's radio signal had to crawl home from more than 120 AU away. NASA, JPL, Stone et al., 2013. If you hear 50,000 degrees, your brain instantly pictures a furnace, instant destruction. But space doesn't care about Earth intuition. Out there, Voyager kept talking, because the number 50,000 doesn't automatically mean heat that cooks things. Stay with me here, because by the end, you'll understand how something can be 50,000 and still transfer almost no heat at all. Here's where it gets crazy. The solar system doesn't end with a line. It ends with layers, like a nested set of invisible storm fronts. First the termination shock, then the heliosheath, then the heliopause, and only after that, true interstellar space. Stone et al., 2005, Stone et al., 2008, Stone et al., 2013. The reason these layers exist is the Sun itself. The Sun constantly blows out a stream of charged particles called the solar wind. That wind drags the Sun's magnetic field outward and inflates a protective bubble around the planets called the heliosphere. Far from the planets, the solar wind finally runs into the interstellar medium, thin gas and magnetic fields between stars. When one flow collides with another, you don't get a neat border. You get a collision zone. In the normal picture, the story is straightforward. At the termination shock, the solar wind goes from supersonic to slower and hotter, like a sonic boom made of plasma. Then the heliosheath is turbulent, stirred-up solar wind, where solar and interstellar influences wrestle. Finally, the heliopause is the real dividing line. Solar particles drop away, and interstellar particles dominate. If you're looking for the moment the Sun's bubble stops being home, it's that heliopause crossing. This is where things get strange. Because the edge didn't behave like a clean textbook diagram, and the evidence didn't come from one obvious instrument readout. It came from detective work. Voyager 1 and Voyager 2 launched in 1977, planet missions on paper, interstellar missions by destiny. Decades later, their readings started drifting into unfamiliar territory. The solar wind was weaker, the environment was changing. But the Sun's influence was still there, until it wasn't. In 2004, Voyager 1 encountered the termination shock. Instruments saw the solar wind slow, heat, and change character. Hard evidence that the heliosphere has structure and boundaries. Stone et al., 2005. In 2007, Voyager 2 reached the termination shock too, but at a different distance. Pattern interrupt. The solar system's bubble isn't symmetric. Something is squashing it. Something is shaping it. Stone et al., 2008. Then came the long crawl through the heliosheath, a chaotic region where the Sun's outflow and the galaxy's background environment push and pull. Scientists around the world watched the particle data like a heart monitor, waiting for the signature of the true boundary. In August 2012, Voyager 1 suddenly saw solar origin energetic particles crash, while galactic cosmic rays surged, as if a door to the galaxy had opened. Stone et al., 2013. That looks exactly like a crossing into interstellar space. But here's the cliffhanger. The magnetic field behavior didn't do the clean, dramatic flip many people expected right at that moment. Debate erupted. Was Voyager truly outside or stuck in some weird boundary layer? And then the problem got worse. Voyager 1's main plasma instrument had failed long before. The tool you'd want most, the one that could directly measure the surrounding plasma, was gone. You might be thinking, So they can't prove it. Stay with me here, because this is where the story becomes brilliant. Scientists proved the crossing using 3 clues. Count them down with me. 3. The heliosphere's own particles dropped sharply. 2. Galactic cosmic rays rose and stayed high. 1. The surrounding plasma density jumped to values consistent with interstellar space. Stone et al., 2013. And clue number 1 is the genius move. Don Gurnett's team used Voyager 1's plasma wave subsystem to detect plasma oscillations, ringing in the surrounding medium triggered by shock waves from solar eruptions propagating outward. Those plasma waves revealed density, like tapping a wall and identifying the room behind it by the sound. The inferred density matched interstellar plasma. That sealed it. Voyager 1 had crossed the Heliopause and entered interstellar space. Gurnett et al., 2013. Now the headline number, the 50,000 degree plasma barrier. Here's what that really means. In parts of the outer heliosphere and heliosheath, particle populations can be extremely energetic, often expressed as temperatures of tens of thousands of Kelvin in popular explanations, depending on which particles and which region you're describing. But temperature out there is mostly how energetic are the particles, not how much heat is delivered to an object. The key is density. The plasma near the boundary is unbelievably thin. Heating requires collisions, tons of particles slamming into you and dumping energy. So even if the particles that exist are extremely energetic, there are so few of them that the total heat transfer is tiny. Analogy. An oven is hot because you're surrounded by trillions of molecules constantly hitting you. The heliopause region is more like a near-empty room with a few ultra-fast ping-pong balls. The temperature number can be enormous, but the heating is almost nothing. That's why Voyager doesn't melt. It's why 50,000 Horndigi sounds like hell, but behaves like vacuum. Satisfying, right? But it raises a new question. If the boundary is real, why did Voyager 1's magnetic signature look messy? Just when you think the story is settled, the second twist hits. Voyager 2. In November 2018, Voyager 2 crossed the Heliopause 2, and unlike Voyager 1, it still had working plasma measurements, letting scientists directly see the solar wind fade toward zero at the boundary. Stone et al., 2019. Nature Astronomy, 2019. That confirmed the crossing with a cleaner instrument set. But the details didn't match. Voyager 1. Voyager 2 crossed at a different distance, and the transition behaved differently. Meaning the heliosphere is a living boundary, shaped by the interstellar magnetic field, and changing with the Sun's 11-year cycle. The edge isn't fixed. It breathes, it dents, it shifts. Then comes the controversy that makes the frontier even messier. For years, many expected a classic bow shock, a strong shock wave at the heliosphere's nose as the Sun moves through interstellar space. But IBEX data suggested we might not have a strong, clean bow shock in the simple sense. Maybe more like a gentler bow wave, depending on conditions. McComas et al., 2012. So what is the 50,000 degree barrier actually describing? It may not be one thing, it could be overlapping effects. Hot heliosheath plasma after the termination shock, magnetic draping, and barriers controlling which particles can cross, and neutral atom interactions and charge exchange near the boundary. Different direction, different solar cycle phase, different wall. And that's why scientists still debate the details. We've only pierced the heliosphere in 2 directions with 2 aging spacecraft, 2 needles through a huge, shifting bubble. I genuinely want to know what you think the barrier mostly is. A. Hot heliosheath plasma. B. Magnetic barrier controlling particle access. Or C. Neutral atom charge exchange effects. Comment A, B, or C, and tell me what measurement would convince you. Because this affects all of us. The heliosphere helps modulate galactic cosmic rays reaching the inner solar system, radiation that matters for astronaut health and spacecraft electronics. Voyager didn't just find a boundary, it helped map part of Earth's long-range space weather shield. And bigger than that, it's a template. Every star with a wind likely carves an astrosphere. Understanding ours helps us model how exoplanet systems are irradiated, and what that might mean for habitability. The hopeful part is, Voyager is still out there, still transmitting with fading power, still turning guesses into measurements. And the next generation is lining up. IMAP will map the heliosphere using energetic neutral atoms, and future interstellar probe concepts could reach hundreds of AU faster and map this boundary in 3D. NASA IMAP. So, no, Voyager didn't hit a literal wall of fire. It hit a boundary where the physics is so unintuitive it sounds like science fiction. A place where 50,000 degrees can be real, and still not burn. And that might be the strangest lesson the edge of our solar system has to teach.